In the last two lectures, we started discussions on the modal analysis of continuous systems. Now, this was the performance of modal analysis was found to be essentially solving an eigenvalue problem. Now, today we are going to look at some properties of this eigenvalue problem that comes up while we perform modal analysis of continuous systems. So, let us start by revisiting the modal analysis problem. So, in our last lecture we had discussed the problem of a bar with varying cross section. The equation of motion of this system was given by this, and the relevant boundary conditions for this problem were given by u at 0 is equal to 0 for all time, and on the right boundary we have a natural boundary condition and in order to do the modal analysis we were searching for solutions of the special form or structure so the field variable is expressed as a product of an amplitude function which is a function of x and a harmonically varying time function. Now, we discussed the properties of this solution and we found that the solution is actually separable in space and time. So, when we write the actual solution in its real form, it appears in this structure. So, it was separable in space and time. The other observation is all points therefore vibrate at the same frequency omega, the same circular frequency omega. Thirdly, all points of the system pass through the equilibrium point at the same time instant. The time instant when this temporal function is 0, the whole solution is 0, which means the bar is in its equilibrium state. So, all points will pass through the equilibrium point at the same time. Then we observed that phase difference between any two points on the bar is either 0 or pi. And finally, we observe the existence of nodes, that means points at which u, the amplitude function capital U of x is 0. So, the points, so the properties of the modal solution are known to us. So, once we substitute a solution of this structure into the equation of motion, we obtained a differential equation in terms of this amplitude function and the corresponding boundary conditions. This forms the eigenvalue problem for the system. So, the differential equation along with the boundary conditions. Now, we will represent this in a slightly abstract form in this manner. Where our equation of motion was can be written like this. So, if you write a general equation of motion of a string or a bar in this form, then the differential equation of the eigenvalue problem may be represented in this manner, where lambda is omega square. So, this actually is plus. So, this is the differential equation, and the corresponding differential equation for the eigenvalue problem is given in this form, where lambda is omega square and this k is a differential operator. Say for example, in the case of the tapered bar, mu of x is rho times the area and the differential operator k, which is also known as the stiffness operator, is the spatial derivative of this quantity E A, the derivative of the argument. So, this is the structure of the differential equation of our eigenvalue problem. Now, here as I mentioned here that this is known as the stiffness operator, because this term comes from the potential energy in the Lagrangian formulation, while this term mu of x is the kinetic energy operator, because it comes from the kinetic energy in the Lagrangian formulation. So, suppose for two modes j and k, we can write this differential equation So, for the jth mode, let us say, we can write the differential equation of the eigenvalue problem like this, while for the kth mode, the differential equation becomes this. Now, we are going to, the objective of this analysis is to determine certain properties of the eigenvalue problem. So, let me multiply this first equation with W k and the second equation with W j, and subtract one from the other. Then after some rearrangement, I can write so I am also integrating over the domain of the system. So, I multiplied the first equation with W k, the second equation with W j, subtracted one from the other and integrated over the domain of the problem, and this is what I obtain upon rearrangement. Now, suppose that this integral vanishes. So, let us consider the situation when this property holds. Where this W and W tilde are functions that satisfy the boundary conditions of the problem. If this property holds, then this operator k is known as self-adjoint. So, if this property is satisfied by the stiffness operator, then it is known as a self-adjoint operator. Now, this self-adjointness of an operator is connected to symmetry. So, as you know that this stiffness operator has a corresponding matrix. For example, in vibrations of discrete systems, you have come across stiffness matrix. So, self-adjointness of the stiffness operator is nothing but the symmetry of the stiffness matrix, the corresponding stiffness matrix. So, what are the consequences of this symmetry? As we know that when matrices are symmetric, the eigenvalues are real and the eigenfunctions are also real, and the eigenvectors are orthogonal. So, in a similar manner, we have these properties which can be shown very easily that the eigenvalues are real, eigenvalues and eigenfunctions are real for whenever the stiffness operator is self-adjoint. Secondly, the eigenfunctions are orthogonal. With respect to an inner product that we will find out in the course of this lecture. So, we will be Now, discussing this orthogonality property. So, recall that we had this equation So, if the operator k is self adjoint, then this term vanishes. So, this implies this integral must vanish whenever j is not equal to k. So, which means if I take two distinct amplitude functions modes eigen functions w j and w k, then they satisfy this property that this integral must vanish, and this we define as the inner product of these two eigen functions. And in a compact form we will write this that inner product of two eigen functions can be written in this form, where alpha j is given by this integral. Now, one may normalize this property by appropriately scaling the eigen functions, because as we know that any scaled form of this eigen function is also an eigen function. So, we can scale appropriately to have orthonormality of the eigen functions with respect to this inner product that we have defined. So, here this w j hat is w j over square root of alpha j. So, here we have orthogonality with respect to the inertia operator. So, if you consider that this mu of x represents the inertia operator, then this orthogonality is with respect to the inertia operator, and correspondingly we can write so for the jth mode, this is the differential equation. So, if I multiply this equation with, so this can be written also for the hat eigenfunction, the normalized eigen function, and if I multiply this with w k hat and integrate, so this shows that the eigenfunctions are orthogonal also with respect to the stiffness operator k. Now, what are the implications of this? So, what is the physical implication of this orthogonality with respect to the inertia and the stiffness operators? So, the implication is that there is no exchange of kinetic or potential energy between the eigen modes. So, the physical implication is that there is no exchange of kinetic or potential energy between the eigen modes. And this orthogonality property is also very useful, as we will see in due course, for solving initial value problems or other problems related to continuous systems. And this orthogonality we have already come across when we discussed about vibrations of modal analysis of strings. Next, we discuss some examples. And we will determine the orthogonality relations for these examples. So, we once again go back to this bar with varying cross section and follow the steps that we have done in detail. So, our eigenvalue problem Now, let us check that this stiffness operator that we have here is really self adjoint. So, what we have to show so this we have to show. So, we have to show that these two are equal where u k and u j are two eigenfunctions of this eigenvalue problem. So, we start integrating by parts, let us say from the left hand side. So, we take this as the first function and this as the second function. This is what we obtain, and here I will integrate by parts this term once again, and here I will use the boundary conditions. So, the boundary terms here that I have, so this term will be evaluated at L and at 0. Now, at L u prime at L must be 0. So, this term must vanish at L and u 0 is 0. So, u k at 0 must be 0 because these are eigenfunctions and they satisfy the boundary conditions of the eigenvalue problem. So, this term is actually 0. So, we are left with only this term, and this I will integrate by parts once again. Now, with the same reasoning as we had here, this term, these boundary terms must also vanish. So, we are left with which is nothing but the right hand side of this equation. So, we have shown that this operator acting on So, we have shown the self-adjointness of the stiffness operator of a tapered bar. So, we can write this orthogonality in terms of the inner product as we were defining. For the tapered bar. Next, we are going to look at the hanging string. Or hanging chain. So, for the hanging chain, the eigenvalue problem read this. So, in this case the stiffness operator is given by this term, and in a similar manner you can check that this self-adjointness property holds for the stiffness operator of a hanging chain. And once you do use this this property, you can derive the inner product of the eigen functions of a hanging chain with respect to which the eigen functions are orthogonal. So, let me just write down this eigen function that we had already derived. In a previous lecture. So, this is the structure of the eigen function of a hanging chain, and they satisfy the orthogonality relation in this form, where so this alpha j is the square of the eigen, say the jth eigen function, and integrated over 0 to L, and this turns out to be where this j 1 is the Bessel function of order 1. Now, let us consider the example of a uniform bar which is coupled to a harmonic oscillator. Which we had discussed in our previous lecture. So, the eigenvalue problem for this system was written as as obtained in our previous lecture. So, once again for mode j and mode k, we can, so these are the two differential equations and these are the boundary conditions for the bar. So, for the modes j and k, we can write now we will once again multiply this with the first equation for the bar with u k and the second with u j, subtract and integrate over the domain of the bar, and upon rearrangement you can very easily obtain So, there are few standard steps. So, to obtain from here to here, that can very easily perform and come to this condition. Now, if you integrate by parts, let us say this first term. So, integrate by parts this first term 2 times and use the boundary conditions for the boundary terms that you generate, then you can check that expression reduces to So, we are integrating this term by parts 2 times. So, at the end of the integration by parts, this term will be exactly same as this. So, that will cancel off, but we will generate 2 boundary terms with single prime, and that we have to replace that we have to use this boundary condition. So, this boundary condition, once you use that, you will ultimately come to this expression. Now, when j is not equal to k, and considering that omega j is not equal to omega k, there are no repeated eigen frequencies, then this bracketed quantity must vanish, and this, if you check, this can be written as here I have replaced these quantities by y j and y k, which we have obtained these expressions before. So, this is our inner product. Remember that in the case of a discrete of a hybrid system in which we have a continuous and a discrete system, we had this eigen function vector which we had discussed in the previous lecture. So, here we would say we will write the inner product in this form, where the inner product is now defined in this form. So, you see this is not a trivial or a simple inner product that we obtain for other systems. So, here we this procedure you have to follow in order to determine this structure of this inner product, how this inner product is calculated based on the eigen functions. So, let us summarize what we have studied today. So, we had revisited this modal analysis problem and the eigenvalue problem. Then we looked at the properties of the modal solution. Then we discussed about self-adjoint operators and the consequence of the stiffness operator being self-adjoint. These are real eigenvalues and real eigenfunctions. Then we have discussed about the orthogonality property of eigenfunctions, and we have determined the inner product. We have outlined steps to determine the inner product with respect to which this orthogonality property holds, and we have looked at the implications of the orthogonality property of eigenfunctions. So, if the eigenfunctions are orthogonal, that implies that there is no exchange of energy, kinetic or potential, between the eigenmodes or eigenfunctions. So, with that we conclude this lecture.